explain. So I just want to tell you, usually these numbers much better. 25% wrong, 17%, about 50% confused. It's not a regular response, but for special relativity, it's kind of is. It just proves again that special relativity is a special topic. And here some of your responses, and in yellow responses expressing kind of, again, a doubt of confusions, and we can see roughly 50-50 between a confident response and a not so confident one. So our goal today is to try to make you feel more confident. Well, first of all, in real life, we never actually deal with the processes happening at really high speed. And what Albert Einstein realized, that light is a very special matter, and whatever we actually know is the result of measurement, and any measurement in a way involves light, at least in thought experiments we always can make. For example, if I want to measure the width of this table, what would I do? I would have to take a ruler, because I need a measuring device. And measuring procedure requires me to place the ruler against the table. That's what any manual would tell you. But that's not the rest, not the end of the measuring procedure. There is something else I have to do. What do I need to do in the end? If I want to know how wide is this table, and I have a ruler and I place it on the table, what do I need to do next? Anyone? Well, the ruler is set to specific units. We could use meters, millimeters, centimeters. On a ruler, you have all numbers already prepared for you. So you just take the ruler, you place it on the table, across the table, and what's next? You have to look at it. Because unless you look at it, you don't know the numbers. And when you look at it, you're using light. But in our everyday life, the distance light has to travel is so short, so for us it happens practically instantaneously. So we don't think about it. However, at high speeds, since light has a limited speed, measuring procedure now is important. And first of all, Einstein said, well, we cannot agree on anything anymore. Everyone has to measure, well, specifically wherever that person wants to measure. And everyone has to use at least one procedure which is kind of the same and universal for everyone. So the easiest way is using light. This is a very simple measuring procedure. You shine light at something, then it reflects back, you register time. This is what is happening for you, not over there. Here, you have a laser pointer, you have your clocks, you look at the clocks, you have a photocell which registers light reflected back. So at one time you start the beam traveling away from you, then at another time it comes back to you, and you say, okay, since light travels at 3 times 10 to the 8 meters per second, now if I know these numbers and I know the speed of light, I can easily calculate how far that object is from me. And another thing, I can easily calculate when light hits that object. It's supposed to be between the instant light goes away and it comes back. And now, with this kind of procedure using light, we can look at all the processes in the universe around, and different people use, well, the same procedure, but in order to communicate to each other, they also have to synchronize their measurement. They have to use the same clocks, they have to use the same rulers, otherwise we can't agree on anything. And the easiest way to do that is, well, you can put all physicists in the same room, give them all the same ruler, and then they can go away in all the places. However, after that, no matter what they measure, they're going to be using the same measuring devices, the same measuring procedures. And after that, when everybody agrees on the procedure, everybody wants using light, turns out things are not so simple as we used to think. Well, in special relativity, first, everybody has to agree on we can say fact, we can say principle, we can say law. Agree on that postulate all laws work absolutely equally in all reference frames as long as those reference frames don't have any acceleration. If you remember, a frame like that has a name, inertial frame of reference. Basically, it means that anyone who is traveling in the universe with constant velocity would be doing any kind of measurements, and everybody would derive from those measurements exactly the same laws, exactly the same equations for force of gravity, exactly the same equations for Coulomb's force, etc., etc. And basically it says that if you are in a closed room with no window like this, no matter what you're trying to do, no matter what experiment you want to make, you can't, it's impossible, you can't make a conclusion. Either you're at rest relative to other objects around, or you are moving with constant velocity. There is no experiment which will give you that information. You have to make a hole and look outside. In that case, you can compare your location with stars around. And a second postulate principle says that, again, everyone, no matter what, must get exactly the same number for speed of light. Well, as long as that observer is traveling at constant velocity relative to stars, everyone should get exactly the same number. Speed of light is a universal constant. And these postulates kind of seem fine. However, if you start applying logically these two laws, turns out a lot of things we agreed on we cannot use anymore. Well, for example, we know velocity is relative. So if you have an object which is traveling relative to another object, which is traveling relative to another object, what usually we do? That's what we do. Here in this example, there is a train traveling relative to you. So you can measure the speed of this train. Inside this train, your friend Ben, with an air gun or something, so it shoots another object or throws, doesn't matter. So this object has speed relative to the train has a speed relative to you. To calculate the speed of this ball relative to you, that's what we use to do. Turns out this is plain wrong, because it violates the second postulate, which says that speed of light must be equal to 3 times 10 to the 8 for all inertial observers. And let's imagine that this guy using a flashlight instead of this gun. What would happen? This equation would give us a result which violates our agreement on speed of light. So if this would be light, that speed would be equal to speed of light relative to this guy. And if you want to use this expression to calculate speed of light relative to you, you would have to write this. So if this number is 3 times 10 to the 8, relative to you, you would have to get a larger number, which is impossible because the postulate says you also must measure exactly the same number. So this law doesn't work and we have to modify it. What else is wrong? Well, we used to think that if we measure distances, as long as we use the same ruler, we get the same result. So if Ben measures the length of the couch, the train, maybe coach, doesn't matter, measure the length of something, and you, with your measuring devices, laser pointers, clocks, trying to measure the length of the same moving train, that's what we used to think it's going to be. Turns out it doesn't work that way. This is wrong again. And another thing which doesn't work anymore, which is wrong, is if Ben measures time for some process, like how long it takes for the ball to reach the floor, and if you would be measuring the time for the same process, that's what we used to think. But again, at high speeds, that doesn't work anymore. What works? Well, that's a different question. But first of all, we have to say something. What would be the same for you and Ben? If we cannot say length is the same, time is the same, something has to be the same. Otherwise, we just can't compare anything. Turns out there is something which is the same in all reference frames. This combination of variables stays the same. You've seen it in the movie. We call it a space-time interval. And it's an interval, so it's related to 2 events. So if you are looking at world around, and something happens at one point at one time, and then at another point at another time, you can calculate the distance between 2 events, you can calculate the time interval between 2 events, and you can construct a combination like that. You can calculate this thing. And if another observer traveling at constant velocity, looking at the same events, that observer has its own distances, its own time measured. However, if he calculates the same combination, the result is going to be equal to yours. So, we can use this fact to answer many different questions. Well, first of all, in our problems, we're going to use only one-dimensional situation, so no y, no z. That's our space-time interval. And this is the problem from precession quiz. And again, remember, a number of wrong answers was unusually high, unusually relative to other topics. So let's quickly take a look at this situation. So, what we have is you and two planets, A and B. This planet is 9 light years away. Well, first of all, what is a light year? You need to know a definition. It's a new and convenient unit to measure distance. Light year is a distance light travels in a year. That's it. So it takes exactly 1 year to travel exactly 1 light year. So if light travels 20 years, what distance does it travel? 20 light years. That's why it's a convenient unit. So the speed of light could be measured in meters per second. However, the speed of light also equals 1 light year per year. It's just a conversion factor, that's it. Nothing more, nothing else. So, 9 light years. First of all, you have to understand now, it's relative to you only. If there's another person traveling in space, that person would measure most probably a different number. Only another person who is at rest relative to you would get the same number. So everything now is relative. And for this planet, 6 light years. And you're looking at the sky and you see an explosion. Well, first of all, when you see that explosion, that means it actually happened some time ago, because it took some time for the light to travel towards you, right? So how much time did it take? If you know that distance is 6 light years, that means the explosion had happened 6 years ago. If you know that the explosion happened, well, here, that means light had to travel 9 years until it reaches you. So the explosion actually happened 9 years ago, then you see it. So now for each event, an explosion number 1 and explosion number 2, you can assign 2 numbers. For 2011, star B, it was 6 light years ago, so time was actually 211 minus 6, and distance from you is 6. For this explosion, when did it happen? So you see it in 2009. However, the star is 5 years away, so it happened actually 9 years earlier, and the distance from you to this star is 9. So now for each event we have 2 numbers, time coordinate and x. And now you can calculate space-time interval. Space-time interval, well, space-time interval squared is easier to calculate than squared. It's supposed to be equal to c times delta t squared minus delta x squared. If you're using meters and seconds, you would have to use 3 times 10 to the 8 for speed of light. However, if you use light years per year, that means speed of light equals 1. Delta t equals, well, that's going to be 2000, that's going to be minus 11, what is going to be 2005, correct? So delta t is 5 squared minus delta x 9 minus 6, 3 squared. 25 minus 9, 16. And you take square root of that. So space-time interval for this pair of events equals square root of 16, 4. And now you say, let's assume someone else is looking at these events. Well, what's good about space-time interval, for all other observers, it has to be 4. So you just have to set it up. I'm not going to do this part, the last one. This part, B, is important because it's related to some of problems. What is happening here? Another person actually sees these events happening at the same location. Well, how can it be? Well, that's you, that's planet B, that's planet A. So that person might be traveling relative to you. But from his point of view, he is at rest. And from his point of view, stars traveling relative to him. And it turns out when the star, the A, passes this observer, the explosion happens. And then they keep traveling. Star A moves away, star B is at exactly the same location relative to this observer, and the explosion is happening at that point. So relative to this observer, these both stars exploded at the same location. So, well, of course, it could happen only for specific speed. We would calculate the speed. It doesn't really matter at this point. What is important that now, for this observer, well, measures different time, different distances. For this observer, delta x is supposed to be equal to 0 for these events, because they happen at the same location. So for that observer, space-time interval squared, which is again 4 squared, supposed to be equal to 1. The speed of light is the same for everyone, times time interval measured by observer number 2, not you. So that's why we use this prime squared plus 0 squared. So we can calculate how much time is between these two events, 4 years, from the point of view of that observer. Well, okay. Another example. here you have to deal with planets, and if you read what's happening, Earth, another planet, you are here, of course, and you know from your previous experience that relative to you, distance between the Earth and this planet Zorg is 20 light years. Well, that means it takes 20 years for the light to travel that distance. Now, there is another person traveling in a space ship, and relative to you, Earth, Zorg, relative to you, the speed of this spaceship is 0.8 of the speed of light. 80%. So how long does it take for this person to travel the same distance? Again, it's a standard situation. Relative to you, you know the distance, you know the velocity. You can calculate that. Distance divided by velocity gives you 25 years. Of course, light travels faster, so it takes only 20 years for light, but 25 years for this person to travel from Earth to Zorg. Now we can calculate the space-time interval for two events. First event, the ship leaves the Earth. It happens at x equals 0 and t equals 0 relative to you. Second event, the ship reaches that planet. And it happens at x equals 20 years and time equals 25. So light years, 25 years. We just haven't found. So now we can calculate the space-time interval. Just plug in numbers. Well, here, this is invisible 1. The speed of light in light years is 1. Delta t, 25 minus 0, 25. Delta x, 20 minus 0, 20. And you're taking the square root of the final number. That gives you the space-time interval, 15 light years. And now we can say, anyone else in the universe would be measuring space-time interval between these two events must get exactly the same number. That includes the person traveling in the ship. So, for Isabel, a person in the ship, at the Earth, the ship was here. That's the first event. Zorg, the ship is here. That's the second event. From her point of view, she is at rest, and planets moving relative to her. So from her point of view, the event number 1, she looks in a window and she sees the Earth. And Earth moves away. And she waits and she waits and she waits, and then she looks in a window and she sees the planet Zorg. That's event number 2. We know that the space-time interval has to be equal to 15. Because that's the invariant, the same number, supposed to be measured by all observers. But relative to her now, again, these events happening at the same location. She's looking into the same window. So for her, if we want to calculate how much time it takes from her point of view, that's supposed to be 0. And from her point of view, it takes only 15 years between these two events. So, you're looking at traveling ship between two planets. You're measuring 25 years. A person inside that ship looking at the same planet, and she measures 15 years. How do we call this? In the movies, time dilation. So the relativity theory tells us that clocks, moving clocks, run slower. In this situation, well, 15 over 25, 60% slower. It is compared. If you're looking at your calendar, 25 years ago the ship was moving away. But when a person, the Isabel, in that ship is looking at her clock, for her it was 15 years ago. Time runs slower for her. Well, for many calculations, we sometimes, well, I would say 90% of calculations involve this kind of coefficient. We call it the Lorentz factor. So that's going to be my first question to you. Just calculate the Lorentz factor for this particular example. So the speed of the ship is 80% of the speed of light. So we just need to plug it in this expression and calculate. I'm going to switch to something doesn't match. I printed 30, and I have 30 students. If everybody would take in one, we would have any left. So 30 minus 1, I suppose, right? You still don't have your clicker working. And one more. Well, someone is... Okay, let's see. Answer number 4. What is it? 5 over 3. Yeah. Again, it's a straightforward calculation, very common one. What's good about this number that you can actually calculate the square root exactly. There are two numbers like that, 0.8 and 0.6. When you're using 0.8, 1 minus 64 is 36, square root of 36 is 6. If you're using 0.6, you get a similar kind of calculation, so try it out at home. How do we use this number? Well, this is one of the examples. We can use it to calculate the time dilation. First of all, if you look at the graph for this coefficient, for this factor, well, in many problems, we don't actually care about actual speed. What's important is the ratio between the speed and speed of light in vacuum. So, and if you calculate this Lorentz factor, this is how it looks like. For really slow motion, the value of gamma is practically equal to 1. So at low speeds in our everyday life, this factor is practically 1.0000, and those decimals don't make any difference. Only when speed is really high, this factor now makes difference. Now, this is another way to calculate what would different clocks show. In our example, one person is at rest. Well, that person thinks he or she is at rest. Another person is traveling relative to the person number one. So, if you want to relate the time measured by one observer and another observer, the most confusing part usually is which time is which. Yeah. Who has to use, you or Ben has to use this time interval or that time interval? The answer is this. By definition, a person in the moving system measures time which we call proper time. So here, relative to them, two events happening at the same place. In that case, this is the time interval between those two events. Relative to you, if you're looking at those events happening at different locations. And if you were measuring time between those events, your result would be this one. So, the problem is, it's all relative. So, the Ben might be measuring time using his clock. And in that case, let's say two events happening at the same place relative to you. So you're looking at something here, and something happens here. In that case, your time is supposed to be this time, and Ben is moving, relative to you. But now you have to think that you are moving relative to Ben. So, relative to Ben, those events happening at different locations. And in that case, this is his time. So, if you are looking at Ben's clock and you think his clock runs slower because the moving clock runs slower, absolutely identical thoughts happening in Ben's head. Ben is looking at you. You moving relative to Ben. And he thinks your clocks run slower. So there is no special reference frame best than other. Everybody is absolutely equal. You're looking at Ben's clock and you say, okay, your clock, you call him and you say, your clock is wrong. It's slower than mine. It takes only, it's already a year here, but your clock shows only 6 months. So 50% of my rate, 50% slower. However, Ben disagrees. He calls you and says, no, it's your clock slower. Who is right? Both. Well, now, if you know, for example, the rate difference, you say Ben's, well, you're looking and you say Ben's clock is running 90% slower than mine. In that case, you can actually calculate the Lorentz factor, and you can actually calculate, well, how fast he's moving. Because as long as you're saying that, you can relate the any time interval measured by your clocks and time interval measured by Ben's clock, and not so. For you, his clocks run slower. So the rate of time in his reference frame is a fraction, 90% of yours. If you are calculating well, time dilation between Ben's clocks and your clocks, you would have to use this equation. If you combine these two equations together, well, actually, Lorentz factor is always greater than 1. Always, right? So it's another hint to you how you should write this equation. Because if you are looking at Ben's clock is moving relative to you. Moving clocks run slower. If they run slower, so you have to take Ben's time interval and multiply it by a larger number to get yours. So that gives you the way to calculate how fast this person is traveling relative to you. However, of course, Ben would say you travel at that velocity relative to him. Well, so if you are looking at Ben's clock and relative to you, your time tells you this number of years. In that case, you can calculate that Ben would experience only a fraction, this fraction of those years. He would be younger relative to you. If Ben is looking at your clocks, and Ben says, well, in a telescope, Ben says that you would get this number of years older, in that case, relative to Ben, his clock would show a larger number of years. Because you would be moving relative to him. Your clock now should be slower. And his clock should have a faster rate and show more years. Well, so in this situation, we know the answer. We know the answer, but how would we calculate it again? Relative to you, it takes 25 years between those two events. Relative to Isabel, who is traveling in the ship. So her time runs slower than yours. So for her, that should be 25 years divided by the gamma to make it slower. So 25 years divided by 5/3, that's going to give you 15. Again, the same result, of course. But sometimes this calculation gives you the result faster than applying space-time interval. Another example of time dilation, a very important one, because everything which we say about rockets and people is kind of speculation. Well, not everything. Some experiments have been done with an atomic clock traveling around the Earth in a plane. But for real persons, it doesn't make a big difference here, because we cannot make a ship traveling at 90% of speed of light, at least for now. So this is a theoretical question. What would happen to a person inside the ship? This is the actual experiment. You know, people run it now for years. There's a particle, we call it a muon, which actually decays very quickly if it is at rest relative to you. So you take a muon, you place it on the table, you look at it, and And in 2.2 microseconds, it decays, it disappears. There is no muon, there are different particles after that. So, this particle, let's say it travels at some speed. Speed equals distance over time. If this particle would decay in 2.2 microseconds, at that speed, it would travel distance 60 meters. So you would actually calculate the speed of that particle without time dilation. Because you have a measuring devices counters, and you can counter, okay, if muon created here, cosmic rays create muons, and in 66 meters it disappears. In real life, that's not what's happening. In real life, that very muon actually travels 10 times larger distance before it actually decays. Why is it happening? Well, it happens because in his own reference frame, for the muon, his time is 2.2 microseconds. But for us, that time will be different. To calculate that time, to calculate how much time the muon lives in our reference frame, we would have to calculate 2.2 microseconds, and we would have to multiply by the Lorentz factor, because for us, it's a longer time interval. Well, of course, 6600, the speed is supposed to be the same anyway. So we could actually calculate everything we wanted. Well, the factor clearly is supposed to be equal to 10. As if you compare the time in our reference frame and the time in muon's reference frame, the difference is 10. If you know the factor, you can calculate the speed. Again, well, 10 equals 1 over square root of 1 over v over c squared, c squared. And of course, you get exactly the same result again, well, almost exactly the same result again, the same speed supposed to be. But this experiment tells us that time is indeed different for different persons. If a tiny observer would be traveling on the muon, that person would live 2.2 microseconds. That's it. However, so the proper time would be 2.2 microseconds. However, because of the time dilation relative to us, that muon lives 10 times longer. Time dilation is not so tricky as it might seem. The most important part is to remember, well, two events happening at the same location should be used as a proper time interval. So, for example, let's say, well, it's a spaceship traveling at 80% of speed of light. Earth, spaceship, so 80% of speed of light, beta is 0.8. We know from our previous calculations the gamma factor is supposed to be 5 over 3. And let's say I don't know. It's a time bomb. Yeah. The guy inside sets it up and it blows. The whole ship. It's alien ship. So we don't want it. And you're watching, and you know that it takes for you 15 minutes before, well, the bomb is set up and it explodes. So what would be the time interval for a person on a ship? Well, we know this is our equation. The question is 15 minutes. Should it go in here or should it go in there? That's normally the question you should figure out first. The rest is just pure mathematics. And to answer that question, we should ask, okay, for which observer? For this guy on the Earth or for this guy in the ship? These two events happen at the same location. Which two events? Well, the first, you set it up, and the second, it blows up. So, relative to you, when you're looking at the stopwatch, at the clock at the bottom, setting up is happening at one location, then the ship keeps moving, and the explosion is happening at another location. So, $15 it is not the proper time. It is not the time which is supposed to be multiplied by gamma. That means in this particular example, 15 minutes is time you are measuring. Relative to you, these events happen at different locations. However, now you can say how much time does it take relative to the observer traveling on a ship. Well, 15 equals 5 over 3 times this. And that's going to be 3 times 15 over 5, 9 minutes. Which agrees with our usual saying that moving clocks run slower. You could ask, okay, when you were preparing this bomb, how much time did you give to this guy? So that's a different question. That's the same kind of device. And now that would be racing relative to you. So relative to you, the time interval between these two events now should be equal to the time interval when that observer had observed. So when you were preparing these clocks, you were setting it up to 9 minutes. Then you gave it to this guy. And of course, for that guy on the ship, the explosion happened in 9 minutes. But for you, when you were looking at that moving ship, these two events have been divided by 15 minutes. Well, another phenomenon related to fast motion is lag contraction. Contraction is happening when you're moving at a fast-moving object. So you're looking at a meter stick, it's 1 meter. However, if you now give this meter stick to a guy who takes it in a ship and flies with it, well, the guy will be looking at this meter stick and he will see 1 meter. Because, again, relative to him, this object will be resting. However, now, relative to you, this object will be moving. So if your trying to measure the length of that flying meter stick. That would be your way to find it out. So in that case, it would be shorter for you. So let's say, again, the ship is traveling at 80% of the speed of light. Well, first of all, actually, we had calculated just a minute ago that on the ship, time travels slower. Gamma equals 5/3. So 3/5, 0.6. That's your time on a ship. The rate of time is 60% of yours. Okay. Now, however, now the length measured by you will be also, well, 1 meter divided by gamma, 1/5/3, 3/5, 0.6. That meter stick for you will be only 60 centimeters long now. What do you think a guy on the ship measuring, looking at your meter stick? Well, relative to that guy, your meter stick will be moving at the same speed in opposite direction, but the speed is the same. So if that guy wants to measure the length of your meter stick, that guy gonna measure exactly the same number, because now his meter stick gonna have a proper length, but yours, which is moving relative to him, gonna be shorter. And there is well, I just said this. There is example which I took from Wikipedia. You have it in your notes. It again is about traveling ship, and it's related to length contraction and time dilation. Remember, like particles also traveling and decay over time, same thing. Another very important physical variable we use always to describe physical phenomena is energy. So it turns out that energy is also relative. Different observers would measure different values of energy for different situations. And we know that when a particle is moving, we can describe one of its property in terms of momentum, T. And again, since velocity is relative, momentum is relative. However, good for us, the fact good for us is that there is an invariant. There is something which is the same for all observers. Like space-time interval is the same. Another combination, this combination, also remains the same for all observers. Well, unfortunately for all of us, different textbooks use different notations and different, even different names for the same things. So, in some textbooks, this equation doesn't have this knot here. In some textbooks, this equation has a knot here. Well, for us, in our course, M is what some people call rest mass. That's the mass which we measure when the particle is at rest relative to us. And of course, anyone in the universe will be measuring the same rest mass for the same particle. So that's an invariant. And if you multiply by speed of the light squared, we get the amount of energy related to that amount of mass. So some call it rest energy, some people call it mass energy. What's important is, if the particle is moving, it also has, in addition to this energy, a kinetic energy. So the question is, how would we calculate kinetic energy now? Now, kinetic energy is not mv squared divided by 2. That's just wrong. Now, if we want to calculate kinetic energy, we have to do this. If we know the mass of a particle, and if we know how fast it's moving, we can calculate this energy. Sometimes we call it a total energy, sometimes just an energy. If you're solving the problem and you're not sure what kind of energy is meant, ask. It might be mass or rest energy, or it might be total energy or just energy. And the difference between that complete energy and the rest energy, that's what we call now kinetic energy. Turns out, only for relatively low speed motion, kinetic energy, well, is approximately equal to mv squared divided by 2. However, now, this is an approximation. It doesn't work for fast moving particles. This is the exact way to calculate the kinetic energy. Well, we also have to use a new definition of momentum. Turns out, we can't just use mv anymore. For fast-moving particles, it's a Lorentz factor mv. That's what we call a momentum now. And, well, the good thing is, if we use this expression combined with this expression, we got a very simple expression for total energy. So for kinetic energy, it's going to be just gamma mc squared minus mc squared. Now, sometimes we don't really need to know the actual mass of a particle. So what can we do? We can combine these two expressions. So we have gamma m in that expression, and we have gamma m in this expression. So we can say that P over V is supposed to be always equal to E over C squared. Or we can multiply by speed of light. This is one of the expressions which sometimes just give you a shortcut to the particular calculation. As you probably know, Professor Rolf is a well-known particle physicist. So he knows everything about particles. And he wants you to know everything about calculating different things. So he gives us some shortcuts for some calculations. Like here, it's an example from a new handout. First of all, if you read it, there is a new unit for energy. MeV. What does it mean? Well, the capital M always means mega. Mega means a million. So this is 10 to the 6. What does EV mean? Anybody knows? Electron volt. That means electron volt. And electron volt equals what? Different words, meaning and equal to. Yeah. Electron volt is just a name. However, we, just in case, need to know how to convert it into joules, actual SI unit. So, we don't have to do it very often, but we just need to remember 1 electron volt is that kinetic energy which one electron gets after traveling, potential difference 1 volt. So, to calculate how much energy we get, we just have to apply our well-known equation for potential energy of a charge in the field. The charge equals 1.6 times 10 to the negative 19 coulombs times 1 volt. That gives 1.6 times 10 to the negative 19 joules. Just in case. And of course, the textbook gives you the same conversion factor. So here, a momentum is given as 1 mega electron volt over C. What do you think this C stands for? No, the coulomb would be a capital C. This is just a little c. The same little c as this one. What does this c stand for? Speed of light. Same here. This c stands for speed of light. So what we have here is the momentum equals 1 mega electron volt divided by speed of light. That's how physical particle physicists like to write it. Or you can say that P times C, this product, equals 1 mega electron volt. Well, and that gives us the way to convert this non-traditional unit into a regular unit for the momentum. This is just a conversion. Yeah. Not a problem on calculating anything. It's a problem on conversion. 1 mega electron volt. This is a conversion factor to mega electron volts. Speed of light over speed of light. Calculation is done. Another example, very interesting example. Let's say that a proton traveling so fast that its kinetic energy is 300 giga electron volts. What does giga stand for? Well, so the question is, calculate the speed of the proton using the standard classical expression for kinetic energy. If we could use it, we would have to do this. And turns out that would give us the speed of the proton 25 times faster than the speed of light. Just a straightforward calculation. Just plug the numbers in and do it. Which means for fast-moving proton, that expression is just wrong, because nothing can travel faster than the speed of light. Well, this is a neat example. What if a particle doesn't have any rest mass? Do you know a particle which doesn't have any rest mass? If the particle doesn't have rest mass, means it never stops, it's always moving. Light, always moving. So this is basically about light. And if we use our expressions for momentum, mass, and energy, this term is 0. That gives E equals Pc, which tells us that this particle must be traveling at the speed of light. That's it. So when the particle doesn't have any mass, it must be traveling at the speed of light. And vice versa, if you set V equals C, in that case your calculation immediately gives you cannot have any mass. So only massless particles can travel at the speed of light, which means any particle with any rest mass, even slightly greater than 0, can travel at the speed of light. Never. So the relativity theory gives a limit on the speed for everything in the universe. Nothing can travel faster than the speed of light. Well, some physicists argue maybe in the future we'll find a way to overcome that limit, but so far we don't know. Well, this is just an example of calculation of total energy, or we call it energy, for the electron traveling at 80% of speed of light, which means V equals 0.8 c, or beta equals 0.8. So that gives again the same value for the gamma factor. However, another thing which is very common in particle physics is this number. But it's not a bomb. If you take the mass of the electron, any table gives you 9.11 times 10 to the negative 31st kilograms in kilograms. And if you calculate the rest energy of electrons, you just have to multiply by speed of light squared. And if you convert joules into electron volts, this is going to be the rest energy of an electron in mega electron volts. So in this calculation, we just use this fact. The rest energy of an electron equals about a half of a mega electron volt. And if we know the rest energy, we just need to multiply by gamma. That gives total energy. What do we do now to calculate kinetic energy? Kinetic energy, by definition, is total minus mass energy, rest energy. So if this is the rest energy and this is the total, kinetic is 0.8 minus 0.5 mega electron volts. Why do we like using mega electron volts? Because numbers don't have any 10 to the negative something. It's a simple number, 0.8, 0.5. So that's what makes it convenient to use. Well, some more examples. Any questions?